All right, let's just jump right in. We are about to unpack one of the most profound, honestly, one of the most mind-bending ideas in all of science, Albert Einstein's theory of general relativity. And it's a theory that completely rewrites the rules for something we feel every single second of our lives: gravity. And right off the bat, here it is, the core idea, the one sentence that changes absolutely everything. Gravity isn't some invisible rope pulling things together. Nope, it's the very fabric of the universe itself, curving and bending and telling objects how they're supposed to move. I mean, think about that. It's a completely radical shift in perspective. Okay, but that immediately brings up a very simple and totally fair question. If there's no force pulling that apple down, why on earth does it fall? Why don't we all just float away? Well, to answer that, we've got to follow Einstein into his most famous thought experiment. He actually called it his happiest thought, and it was the big aha moment that unlocked the entire theory. And it all takes place inside a simple, windowless elevator. So imagine you're in this elevator, way out in deep space, miles from any planet's gravity. If a rocket suddenly starts pushing that elevator upwards, what happens? You'll feel your feet get pressed into the floor, you'll feel heavy, and here's the absolute key. That feeling is completely, totally indistinguishable from just standing still in an elevator on the surface of Earth. From inside that box, you have no way of telling the difference. Now, let's flip it. Let's say you're back on Earth and the cable on your elevator snaps. For those terrifying few seconds, you are in free fall. You, your phone, anything else in there with you, you'd all be floating, completely weightless. And that feeling? It's identical to just floating in that same elevator out in deep space with the rockets turned off. This whole elevator ride brilliantly illustrates the core insight, which Einstein called the equivalence principle. And the implication is just staggering. If you can completely cancel out the feeling of gravity just by changing your frame of reference, by free falling, then maybe gravity isn't a force at all. Maybe it's just a feature of the geometry of space-time itself. Now, this was way more than just a clever mind game. This new geometric view of gravity made some stunningly precise predictions that scientists could actually go out and test. And when they did, well, the results changed science forever. For decades, astronomers were really stumped by Mercury's orbit. It wobbled just a tiny, tiny bit more than Newton's laws said it should, by about 43 arcseconds per century. Some people even made up a phantom planet, they called it Vulcan, just to explain it away. Then Einstein comes along, plugs the numbers into his new equations, and boom, he calculates the exact 43 arcseconds. An annoying little puzzle instantly became a massive win for his theory. But the theory didn't stop there. Einstein also predicted that really massive objects, like our sun, should actually bend the path of light itself. His equations calculated that starlight grazing the sun would be deflected by 1.75 arcseconds. This was a hugely bold prediction, double what you'd get from a simpler Newtonian calculation. He was putting his whole theory on the line. And after that, the evidence just kept piling up. In 1919, Arthur Eddington's famous eclipse expedition proved that yes, the light bending was real. Then came experiments confirming that time itself literally runs slower in stronger gravity. And then, in 2015, we heard it, the actual ripples in space-time from colliding black holes, confirming gravitational waves a full century after Einstein predicted them. Incredible. Okay, so this isn't just about weird planets and distant stars. This theory has a very direct, very real impact on technology that pretty much all of us use every single day. Without it, your world would be a lot more confusing. Your phone's GPS, it works by talking to satellites orbiting the Earth. But here's the thing. Those satellites experience time differently than we do down here. First, because they're moving so fast, special relativity says their clock should tick about 7 microseconds slower each day. But second, because they're in weaker gravity, general relativity says their clock should tick 45 microseconds faster. To get your accurate location, the whole system has to combine these two effects and apply a net correction of 38 microseconds every single day. Without that correction, GPS errors would pile up by about 10 kilometers a day. It would be useless. So, general relativity works for apples and it works for your phone, but where it really shows off its power and its strangeness is in the most extreme environments in the entire cosmos. This is where space-time gets really wild. Let's take two black holes spiraling in towards each other. General relativity predicts their entire cosmic dance. First, you get the in spiral, as they get closer and closer, shedding energy as gravitational waves. Then the merger, this incredibly violent collision. And finally, the ring down, where the brand new, bigger black hole kind of settles down, sending out final ripples like a bell that's just been struck. And this is exactly what our detectors like LIGO have heard. And you know those amazing images we're getting now from things like the Event Horizon Telescope? We're not just looking at some pretty computer-generated picture. This quote says it all perfectly. We are looking at the geometric fingerprints of space-time itself, being warped and twisted around a black hole in exactly the way the theory described over 100 years ago. I mean, the list of things that once sounded like pure science fiction is just incredible. The idea that mass could act like a giant cosmic magnifying glass? Check. Regions of space with no escape we call black holes? Check. Spinning objects literally dragging the fabric of space-time around with them? Yeah, check. And of course, those ripples in space-time itself? All of these have now been observed. And that brings us to a really essential idea. General relativity isn't some historical artifact that we put in a museum. It is a living, breathing theory that is still a vital tool for discovery right now, today. From understanding the entire evolution of our universe in cosmology, to mapping black holes with incredible detail, to opening a brand new window on the cosmos with gravitational waves, Einstein's equations are right at the heart of so much of modern physics. It's not a finished story. It is the engine that's driving us forward. You know, if there's just one idea to take away from all of this, it's this one. Before Einstein, we all saw space and time as this fixed, passive background. It was just the stage where the drama of physics played out. General relativity showed us that the stage itself is an active participant. It bends, it warps, it ripples, all in response to the actors upon it. So general relativity gives us this incredibly successful description of how gravity and space-time work, all the way from falling apples to colliding black holes. But it leaves a deeper question on the table. Why is the universe built this way? Why does this beautiful geometric structure exist at all? Well, that is one of the great unanswered questions that's going to drive the next century of physics.